All right, so in this example, let's actually go through an example illustrating how the integral test works. And for this case, we'll go through the example for this series that we introduced in the previous video, the series from n equals 1 to infinity of n e to the minus n. And as previously discussed, if we try to apply the test for divergence, we will see that this series passes the test for divergence, so it doesn't get weeded out through that test. And we also see that this series actually is not a geometric series test, or not a geometric series, so the geometric series test doesn't apply. So at this junction of the class, our only hope is to try and apply the integral test to basically see what happens. So on that note, let's see what happens. So the first thing for this integral test on our route to actually being able to apply this is we need to make sure that we can apply the integral test. So the first thing we do is we look at our series function and we basically make this more continuous kind of counterpart to this series function. Here our function is going to be f of x times e to the x times e to the minus x. And we're going to test this function 3 different ways to make sure that we can apply the integral test. And those 3 criteria for us to use the integral test are that this function is positive, continuous, and decreasing on a specific interval. And for us, this interval we need to test is the interval from 1 to infinity. And we more or less think about that because our series is also going from 1 all the way to infinity. All right, so let's start applying these criteria. The first criteria we test is whether this function is positive. So again, we're thinking on the specific interval from 1 to infinity. Is this function f of x always going to be positive? Well, x will always be a positive number on this interval. E to the minus x will also always be a positive number on this interval again. So our function is always going to be positive. So it checks out that criteria. The second thing we get to check is to make sure it's continuous. And while looking at this function, so I'll just rewrite the function below. We could also equivalently rewrite this function as x over e to the x, just using algebra. And the only reason I'm doing this is when we're testing this for continuity, or for its continuity properties, this function has no divide by zeros on this interval. So we don't have to worry about this ever being discontinuous. So it's going to pass this check as well. This function is continuous. We don't get any divide by zeros or things of that nature. Now, the third piece of criteria we get to check is whether this function is decreasing. And this is where we get to remember a little bit of our Calc A kind of tools. So remember, if a function is decreasing, its derivative must be negative. So what we're going to get to do is compute this function's derivative. So I'll rewrite it the original way, x times e to the minus x. We'll take its derivative. And since we have the product of 2 functions, we get to use our product rule. So derivative of the first function x is 1, so we just get e to the minus x. And we add to that the derivative of the second function times the first function itself. So the x will remain the same. And the derivative of e to the minus x is a minus e to the minus x. So let's just rewrite this derivative. So we have e to the minus x e to the minus x. Or if we use a little algebra, this is 1 minus x times e to the minus x. All right, so that is our first derivative. And again, in order for this to be decreasing, for this to decrease, we need this to be less than 0. And where do we want this to be less than 0? Well, we want this to be less than 0 on our interval from 1 to infinity. And let's see what happens here. Well, this exponential will always be positive, but for any number greater than 1, this 1 minus x will be negative. So if we have the product of a negative number times a positive number, that overall thing is going to be negative. So it turns out this function is also decreasing. So big picture again, we're sort of doing the buy-in that's allowing us to do this integral test. Our function had to satisfy these three criteria, and we saw that it satisfies these three criteria. So now we can actually apply the integral test. And as we'll see in class, what actually goes on for the integral test is we put the question of whether a series converges or diverges onto an associated improper integral. And that improper integral for us will be the improper integral from 1 to infinity of that function f of x that we just tested the criteria for. So that in this case would be x times e to the minus x dx. And basically, if this integral is a finite number, the improper integral converges, the series converges. If this improper integral diverges, then the series diverges. So let's go ahead and apply our knowledge about improper integrals. So the first thing for improper integrals, we see that infinity hanging out at that upper bound. So we get to introduce a limit. So let's take the limit as c goes to infinity of now the integral from 1 to c of x e to the minus x dx. And now that we've introduced that limit, we can just go ahead and perform the integration the way we normally would. So of course that limit stuff will carry throughout. But the rest of this problem, we just compute the normal fashion. So for us, that means we have to look at what's inside this integrand and ask how we can anti-differentiate it. And well, we have the product of two functions. Neither of those functions looks like the derivative of the other. So integration by parts. So for integration by parts here, we can let u equal x. The du will be equal to 1 dx, which means the dv portion is everything else, the e to the minus x dx, and our v, when we anti-differentiate that piece, will be a minus e to the minus x. So we can recombine all this information. U times v will give us a minus x e to the minus x, and that piece will evaluate at 1 and that upper bound c. But then we subtract off the integral from 1 to c of v times du, which for us will be minus e to the minus x times 1 dx. So let's just do a little bit of algebra here to clean this up. We still have that limit as c goes to infinity out in front of that first piece of the antiderivative, minus x e to the minus x, evaluated at 1 and c. And inside of this integral, we have, well, we have a minus sign from that exponential in front of that exponential there. We have a minus sign out in front, so that results in a positive sign. And then we have the improper, or the integral from 1 to c left over of e to the minus x dx. So what's nice is by applying integration by parts once, we can evaluate what's inside of that integrand, and that is a function that we can just compute its antiderivative of in a straightforward way. So finally, rewriting what we have here, the first piece, minus x e to the minus x. We evaluate that at 1 and c, but then from this last integral on the right-hand side, we'll get the rest of that antiderivative, that's minus e to the minus x, and we evaluate that whole antiderivative at 1 and c now. So again, the big picture idea, from the original series, we took that, we found that function f of x, made sure it satisfied those three criteria, and started using the integral test by starting to compute an improper integral based off of our series function. So we're in the weeds in the middle of doing all of that. All right, so let's plug in those bounds. We're not yet at the point to take that limit. So plugging in the bounds, we have, plugging in the upper bound, we have minus c times e to the minus c, minus e to the minus c, That's the first piece from our antiderivative. And then plugging in the lower bound of 1 will just give us a minus e to the minus 1 minus e to the minus 1. And at this junction, we've plugged in those bounds. We're finally ready to start taking some limits. And just to practice a little bit of our algebra before, all of those e to the minus c's, I'm just going to rewrite that as a 1 over e to the c. So this first term for us will be a minus c all over e to the minus c minus 1 over e to the minus c. And of course, that second term, well, we could recombine some of these terms. So this will be minus 2 e to the minus 1, which is, of course, just some number. All right, let's see what happens when we take that limit as c goes to infinity. Well, oops, already messed up a bit. In those denominators, those should be e to the c's, not e to the minus c's. So let's take those limits. Well, as c goes towards infinity, in that second term, that denominator is getting very, very large. That numerator is staying as a finite number of 1. So 1 over a very, very, very large number, that's looking awfully like 0. In the second term, what's happening though is this denominator, like we just said, is going towards infinity, but also this numerator c is also going towards infinity. So because we have an infinity over infinity looking thing, we get to do some L'Hopital's. So let's do L'Hopital's rule on that first term. So the derivative of the numerator will just, with respect to c, will just give us a minus 1. The derivative of that denominator will just give us the e to the c back. And well, if we look at what we have in that remaining term, we have a minus sign times minus 2e to the minus 1. So that would just result in a plus 2 over e. We wrote it like that. And now let's see what happens in this limit. Well, there are no c's in the second term, so we can just, the limit doesn't really do anything to that. But we see that there's a c in this first term. And again, that denominator is getting very large as c is going towards infinity. That numerator is staying as a finite small number. So this whole thing is going towards 0. So at the end of the day, this improper integral is equal to 2 over e. And now what I want us to stress here is this 2 over e is a finite number. So the improper integral converges. But here's the special thing. But by integral test, the series also converges. So what that means, if we go back to the very beginning of the problem, that series that we started out with, the series from n equals 1 to infinity of n e to the minus n, this series we just found converges by integral test. And the last thing I want us to stress here with integral test is, even though we saw that that improper integral converged to 2 over e, we don't actually know what the sum of the associated series is. So the sum of this series will not be equal to what we found from the improper integral. All we've proven through integral test is in fact that this series converges.